Yeah, so recording has started. So again, good morning to all of you and welcome. So in last class, we have discussed, couple of CMOS fabrication and in between, right? CMOS fabrication steps as well. Before that, I have shared with you one recorded lecture on this layout. And we were also discussing some other thing like ratioed logic, non-ratioed, means ratioed logic and ratioless logic. Right. Then we have also discussed about how to implement the suppose if you have given some Boolean function, how to implement that Boolean function. Then we have discussed about power, different types of power dissipations uh, in CMOS circuit, right? And prior to that, we were discussing primarily we are focusing on the delay part, right? And right, that's what we have primarily focused, right? So I think let us discuss a couple of more things on delay and which are actually relevant from practical design point of view. So here, so far our discussion was only limited to this only one gate, and that is this CMOS inverter gate. Right. So this is the CMOS inverter. We have discussed it so many times, right? This is the load capacitance. So we know there will be one intrinsic capacitance from here as well, right? There will be one intrinsic capacitance or the parasitic capacitance, which will be the coming part from this PMOS and NMOS, right? And this is the load capacitor. Okay, the CL has been contributed by the next stage. Okay, but there will be one parasitic part, you can say like CP. CP is the parasitic part. Right, we have seen all these things and we have seen how to calculate delay and all these things. So this is basically in terms of a single gate, which is a NOT gate or inverter, right? And we have also seen what will be the case if you have a chain of inverters, right? A chain of inverter means, okay, you can individually calculate delay. That is not a big deal, and then just add the delays to find the total delay in there. But on apart from that, we have also seen what should be the criteria to get a minimum delay if you have given a chain of delays, a chain of inverters like this, right? So you have done all these things so far. But suppose if you want to design a practical circuit, you cannot design a practical circuit by using only this inverter, right? You can have an inverter or you can have a buffer by using this, right? So along with this inverter, you can have also NOR gate, you can also have NAND gate, right? Different other gates. So then what will be the criteria? Suppose consider this, okay, consider this circuit. So there is only one path, right, from this input to this output, and this path is like this, right? So this is that path. Then if I ask, like, if this is 10 size, if this is 10 means the size is 10 and it has to drive, it is basically unit is C. Okay, the unit we are saying like 10 means 10 unit of capacitance. What is the unit of capacitance that we always refer in terms of the smallest transistor dimension. So for NMOS, right? So it is basically 10 of that C, and it has to drive, this total power has to drive, is driving a capacitor which is of 20 C, right? Then how we will size it? We know how to size if this total chain is consist of only inverter, but if there are other component, other gates, then how to do that, right? Then that is what we are going to discuss today. Okay, and that is very important from the exam point of view as well as from the practical design perspective as well. So to start our discussion, so I think let us discuss on the couple of things which we have already discussed. Okay, so we have already discussed what is the delay in case of an inverter, right? For a single stage, right? If you say a single stage, we have seen this equation, that is TP delay will be equal to TP naught, right? This is the intrinsic delay into 1 plus uh, C external by this gamma of this C in. Right, we are completely aware of that. And remember this gamma, this parameter, this gamma typically for submicron case, submicron technology, we have considered gamma equal to, so far gamma is equal to 1 for submicron technology, right? So that equation becomes Tp equal to Tp naught into 1 plus C external by this gamma of this C external by C internal, right? So if you recall that we have also discussed that where from this part means TP naught into means this TP naught part is coming. This TP naught is the intrinsic delay part, right? Intrinsic delay. Okay, this intrinsic delay is coming because of this capacitor, right? Because of this CP, right? Because of this CP, this intrinsic delay is coming. So we can also say this is due to parasitic capacitors, right? This is due to the parasitic capacitor, and there is one more component, that is TP naught into this part, right? So you can understand this is TP naught into this part. This is basically due to what? This is because of the CL, right? So this is because of the due to the external load. Right. Okay. So if you have, if you agree with me on this, which is basically we have done, like we have written an equation which we have already discussed, right? So you know this. So in general, if I am, then I can write, in general, we can write this delay. Let's say that we are saying this delay as this D. We can write delay is equal to this P plus F, right? Now, what is this P? P is the parasitic delay, okay, or intrinsic delay. So this P is basically this part, the first part. And what is this F? This F we will call it as effort delay or stage delay. Okay, because it has to drive an external load or maybe a next stage of any other gate, right? So it has to put some effort, right? So it's called this, and for this effort it will obviously have some delay. So we have referred it as effort delay or next stage delay. Right. So this parasitic delay is completely dependent on the gate. That is no doubt. It depends if it is inverter, it completely depends on the inverter, right? Nothing external can influence this. And what is this F? F is the effort delay and the stage delay, right? So it depends what is the next gate, what is the complexity of the next gate. Means what is the capacitor this in first gate has to drive, right? So that is basically this F. Okay. So let me put it again here. This F is the effort delay. Okay. This effort delay, now we'll write like this. Effort delay is equal to G into H. Okay. Now we will we will discuss all these things individually. Now what is okay, before you go to this G, we will see what is H. Okay, what is H? H is the fan out. Fan out, or it is also called electrical effort. Okay, so this H is can be written in general C out by C in. Okay, so H basically what? It is basically what is the C out by C in means, okay, or in other way we can also define it as number of identical gates driven by an individual gate. Okay, suppose if you have one inverter and if this inverter is driving two inverters, right, then this basically says that number of identical gates driven. So basically here, then this H, that fan out, would be equal to 2, right? But remember, if it is the same gate, but if it is a different gate, then in general you have to use, suppose this inverter is driving some another gate, then you have to use this H is equal to what is this C out by C in. Okay. Now here one more term, that is this G. This G is called the logical effort. Okay. This logical effort depends on the gate that you will be using. Suppose if this inverter drives another inverter, then we will see this, then the logical effort would be equal to 1, because the complexity, okay, of this gate and this gate is same in complexity in terms of delay. Just wait for 1 or 2 minutes, you will understand what do I mean by complexity. But if this inverter drives, say, a NOR gate, then the complexity or the delay, okay, in this case would be different. So here this G value or the logical effort would be different. Okay. So let us now discuss in the next page what do we mean by this logical effort. So logical effort, which we are representing here with a symbol G, right? So logical effort, it can be defined like this. Logical effort basically is the ratio, or how to find the logical effort is not a definition actually. How to find it is basically the ratio of input capacitance of a gate to the input capacitance of an inverter that can deliver same current. Please read this thing again and bit carefully. Ratio of input capacitance of a gate, right? Ratio of input capacitance of a gate to the input capacitance of an inverter that can deliver same current. Okay. So I will come back to this, okay, to this writing just maybe in 1 or 2 minutes. So let's consider one inverter where you can see this inverter, right? And say for a particular technology node, right, this PMOS for this inverter and NMOS, this ratio, this width ratio has to be 2:1, because you know that, right? You have to get a symmetrical VTC, you have to get an, right, equal, like a fall in time and equal rise time, right? The symmetrical rise time and fall in. So you have to make the resistance of this PMOS and NMOS same, and depending on the technology node and mobility of electron and hole, this ratio will change, that you know. So but say for a particular technology node we have fixed this width, so it is 2, this is 1. Okay, now fine. Now once we have fixed it, now on the same technology node, suppose you want to make an 2 input NAND gate. So this is the like transistor level diagram of an 2 input NAND gate. I think now all of you will agree with me that here this F, if I say this F would be equal to A dot B bar, isn't it? Right. But here the constraint is we want whatever be the delay for this case, or whatever be the driving capability of this PMOS or this NMOS, eventually the driving capability of this PMOS and NMOS is same. That has to be same for this PMOS and for this NMOS group. Are you getting my point? The driving capability of this PMOS has to be same by the driving capability of this. Okay. Similarly, driving capability of this NMOS has to be same of driving capability of this right? Okay. Let us go one step further. See here. Now here it is a 2 input NOR gate. So if you design 2 input NOR gate transistor level diagram, it looks like this only, right? So 2 input NOR gate. So here too we have to design or make this ratio of P and N transistors such that together this combination will give equal resistance of this inverter. Similarly, this combination should give equal resistance of this inverter. Okay. Okay. Now if I want to ask you, okay, then tell me this thing quickly. what will be the size of this NMOS for 2 input NAND? Anyone, quickly. The criteria is we want the resistance to be same for the pull down network.
Wn equal to P.
Yeah, what should be the width?
Wn equal to 2Wp.
Okay, so let us say only focus only Wn only. So what would be Wn? Shubhayan, it is what would be the Wn value?
It will be halved.
Half. Are you sure? Wn.
Twice.
No, sir. Sorry, sir.
Twice, right?
Same.
It is like two MOS are in series, right? So you have to make the width 2 times so that the resistance, just you can consider it like this. Now, if it is 1, if this resistance is R, right? Now, if you make R and R, so the resistance become 2R, right? So what you have to do, you have to make this width 2. So if you make this width 2, so that means the resistance become R by 2, right? So here, so this means this is R by 2. If you make this width 2, that makes this resistance R by 2. Right? So that way the total resistance of this pull down network would become R, right? Okay, right. So can you comment the same for this PMOS, for this 2 input NOR? So here also see 2 PMOS are in same. So if you have to make the resistance of this total part, the total pull up network same as that of this equal inverter, right? Then what you have to do? You have to make the width of this transistor 2 times. So you have to make it 4. You have to make it 4, right? Then only the pull up network of this and pull up network of this would be equal. Or in other way, we can say that then this pull up network and this pull up network can deliver same current. Deliver same current for charging, right? Or in other way we can say this pull down network and this pull down network can deliver, means can take out same amount of current while discharging, right? Okay, now let us focus on this.
Sir,
Yeah,
sir, for the two input NOR, why did you like in the two input AND we are adding these for A and B, uh, but for two input NOR, why aren't we doing that same thing?
for 2 input NOR why we are doing same thing means you want to ask like why we are doing making 4.
No, sir. I was like asking that for two input NOR, this would become 8, right? By adding these.
Sorry, am I missing something? Like,
No,
Arsh, what is your question? Could you please reframe your question and tell me?
sir, I was asking like for two input NAND, we
Hmm.
put R by 2 and R by 2 there,
Hmm.
and that became R.
Right.
Okay.
Hmm.
And for like in the pull-up network, we want
Right. Pull
two
up.
R,
See,
two,
pull
right?
up network. We are discussing for NOR gate, right? Right now.
Yes, sir.
Okay.
Yes,
So,
sir.
what is the resistance of this inverter? If it is
Two
2,
R.
it is 2R.
Sir, uh, resistance for
Okay. Why we have chosen this ratio?
So resistance is inversely proportional to width every time.
Right. So, why you have chosen this ratio? We have chosen this ratio because so that the resistance of this and resistance of this become equal. So if
yes,
this is
sir.
R, then this has to be R,
Yes, sir.
right? This is because
Yes, sir. I got
the
it.
whole has a, you can say consider like for this case whole has the whole mobility is half compared to
Yes, sir.
electric,
Yes, sir. Yes, sir. I
right?
get it. Yes, sir.
So here it is R, so that means when you make it 4, so then this become 2R. Sorry, this become R by 2, right? This become R by 2. Right. So if you see the total resistance for this pull-up network, that become R by 2 plus R by 2, that is equal to R only, right? Same as this.
Yes, sir. Yes, sir. I get. Thank you.
Okay, fine. Now, if you consider for this case, let's say this pull-up network for this NAND gate. So, can you comment what should be the width?
1.
1, 1. Okay,
One.
because you were thinking it like if you make it 1 and 1, so this resistance become 2 R, this resistance become 2 R, and 2 R in parallel, so that become R. Yes, you are right from what from your perspective, but actually while designing we always consider the worst case. So what will be the worst case? Worst case when these two transistors are in parallel, worst case situation will arise when only one of the transistor is on, right? So that means either this transistor or this transistor is on. Then that is the on worst case, right? So we consider the worst case and we make the transistor sizing accordingly. So that way, if these two or three transistors in parallel, so we'll always consider that only one of the transistor can be one at a same time. That is the worst case situation. So that way, definitely here also one transistor, here also one transistor. So definitely it will be 2, size will be 2. Here the size will be 2, right? Now, if you see here, that is for 2 input NOR gate. To the same logic, here 2 transistors are in parallel. So here also, like worst case situation will arise when only one of the transistor is on, okay, or one of the transistor is being used to discharge, right? So in that case, this size would be equal to the same as this of this, right? So that is 1 and 1. Please check, is this part clear to you or not? Right? Okay. So now let us again come back to this. Okay, whatever we have studied here. So what is logical effort? How do you find it? Logical effort is the ratio of input capacitance of a gate to the input capacitance of an inverter that can deliver the same current, right? So now we can clearly say like the driving capability of this PMOS or this pull-up network and this pull-up network are same. Similarly, the driving capability of this pull down network, this pull down network are also same, right? So this criteria is now valid. So now to find the logical effort of any gate, what we have to do? We have to just take the ratio of input capacitance of this gate and divide it with the input capacitance of this single inverter, right? Okay. Then in that case, what is the input capacitance for this inverter? What is the input capacitance for this inverter? See, 2 unit, right? So whatever be the capacitance here, so everything will be multiplied by 2. So this 2 and here it is 1 unit. So 2 plus 1, so C input is total 3. So it is a 3 unit capacitance. Okay. So what is the unit capacitance here? So let's say that you have connected this V out with A input, right? So what is C in here in this case? It is 2 plus 2, it is 4, right? What is C in here? So let us say again it is driving this A input. So it is 4 plus 1, so it is 5, right? So then how do you find the, you know, logical effort? So logical effort for this gate or this inverter would be how much? It is 3 by 3. So it is equal to 1. Okay. Now let me ask you one question. So this is a basic unit inverter, right? So this is an unit inverter. So this is 1, right? Size is 1. So let me ask you, I have sized this inverter 5 times. Okay. Now tell me what would be the logical effort of this? What would be the logical effort of this?
Sir, can you please explain once again what is the logical effort of the inverter? I mean, how it
Logical
is going.
effort of the inverter is basically the input. See, it is the ratio of the input capacitance of the gate. It can be any gate, including inverter, to the input capacitance of the inverter, provided that they can deliver same current, right? So this is an unit inverter, unit size inverter. Here C in is 3, right? Now with respect to this, if you want to find what is the logical effort of this inverter, then what will happen? These two inverter can deliver same current, so you have to take the input capacitance of this inverter and by input capacitance of this inverter, so it will be 1. Now my question is, this is an unit size inverter, so if I size it to 5 times, okay, or 10 times, then just comment on the logical effort for that case. Please tell me quickly. One only, right? So the logical effort would be 1, because again you see this definition, ratio of input cap of this particular gate to the input cap of this inverter which can deliver the same current, right? So if you make it 5 times, right, if you make this 5 times, then this inverter has driving capability 5 times compared to this unit inverter. So this unit inverter also has to be multiplied by 5 so that you will get the similar driving capability. So that again makes this ratio would be the same, right? The input capacitance for this and input capacitance of this particular gate, this gate, and input capacitance of this gate would become same. So it becomes basically 3 into 5, 15, and for this case it becomes 3 into 5, 15. So it is 15 by 15, it will become equal to 1, right? So you can test it. We have not so far done it for the two input NAND gate and NOR gate, but just to make a general statement, I am making it right now only. So logical effort does not depend on the transistor sizing. Okay, you can make transistor sizing, like make the whole gate transistor sizing like whatever you want, but the logical effort always going to be the same because of this criteria that they should deliver the same current. Okay. Okay, now let us see then for this case what would be the logical effort. So here the input capacitance we have already calculated 4, so it is 4 by the input cap of this inverter 3. Remember, now if you scale it, if you make it 4, if you make it 4, make it 4, make it 4, then this inverter means this NAND gate driving capability is 2 times than of this unit inverter, right? Then in that case you have to make this unit inverter also scale accordingly to match the current, and that basically again if you do that you will always get the logical effort for this 2 input NAND gate to be equal to 4 by 3. Does not matter what is the size. Okay, so for this case, what is the logical effort? It is 5 by 3, right? Okay. Now, let's say we have, and yeah, inverter always can only have one input, right? So, and NAND gate should have like more than 2, like, but it can be any number from 2, 3, 4, whatever you want. So let us say that n input. Okay, so for n input NAND gate, okay, what would be this logical effort? Any comment? For n input NAND gate, what would be the logical effort? Yeah, what about Alisha?
So 2 to the power n plus 1 by 3.
Huh?
2 to the power n plus 1 by 3.
2 to the power, I guess it will not become to the power something. Okay, let us see that.
N
Okay, let
plus,
us see for
n
3
plus 2
input.
by
n plus
3.
2
N plus 2 by 3.
n plus 2
N
2n
plus 2, right. It will become n plus 2 by 3 because it is not difficult. Okay, you can also see, just put here 2. So right, for 2 inputs, so it is basically 2 plus 2 by 3. So let us, if you want to check it for the 3 input, so for 3 input, this would be like this, right? So 3 input is 3 input we are doing 3 input NAND. So I am not doing it like completely, right? It is A, B, C here also. ABC. Right. So again, here you know the sizing would be like 2, 2, 2 only, but here we have 3, right? So here we have 3. So the transistor has to be scaled by what? What should be the scaling here? Yes, Shamukh, can you comment on this?
3.
So 3, 3, 3.
3, 3, 3, right? 3, 3, 3. Right. Then if you see what is the input capacitance, it is 2 plus 3, 5, right? So you make it here 3. So 3 plus 2, so it is 5, 5 by 3, right? Okay. Similarly, for n input NOR gate, this logical effort is given by 2n plus 1 by 3. Just you can taste it. Okay, it's not a big thing, but you can taste it. So hopefully you will get this result only. But in this here, I would request you to notice one thing, that this is also 2 input, right? So both are 2 input NAND and 2 input like NOR. But see the logical effort. For 2 input NAND, the logical effort is 4 by 3. For 2 input NOR, the logical effort is 5 by 3. So from this discussion itself, you can get at least some idea why we should prefer NAND implementation over NOR implementation, because logical effort for NAND is less compared to, so just if I can write it like this, is less than this G of NOR. Okay, for same this. Right, so NAND is a better choice probably from delay point of view. Right, okay. So here this we need, so let us fill it here so that we can look into this table again and again and complete our like design part. So for inverter logical effort, so here we are plotting the logical effort, means we are saying a lot, like for logical effort of this inverter always have only one, can have only one gate only or one input only, so that way it is inverter logical effort is 1. For NAND, it starts with the 2 input, right? 2, 3, 4. So for 2 it is 4 by 3. For 3 input it becomes 5 by 3. We have checked it. For 4 it becomes like 6 by 3. We have also have general equation here. For NOR it is 5 by 3, then 7 by 3 and 9 by 3. Okay. So is this logical effort clear to you? So logical effort, in other words, is basically it indicates how much hours a particular gate is at producing the output current compared to an inverter, right? That is basically it indicates. Okay, if you have understood how to find and what do you mean by this logical effort, then let us move to the next step. Okay, so let us see first here before. So we are trying to find the delay, right? So we have here P plus F component. F is equal to GH, right? F is equal to GH. Now we have seen H. We have understood somewhat whatever. We have seen this G, logical effort. We have understood what is H. So we left out only the parasitic delay. Again, parasitic delay for inverter we already know. Now let us focus what will be the parasitic delay for other gates. Okay, so the parasitic delay, right? So parasitic delay, what do you mean by this parasitic delay? So parasitic delay of a gate is the delay when this gate drives no load. That means after this, suppose if it is an inverter, there is no load. Means basically this inverter is driving the intrinsic capacitance only. Again, if it is a 2 input NAND gate, then also you have not connected any load, right? No load cap. Okay, only the intrinsic one. Okay, only C intrinsic, right? Okay, now again we have considered the ratio of PMOS to NMOS with 2:1, so that makes this 2, this 1. Okay, right. Then can you comment what would be the parasitic capacitance for this inverter? So what do you mean by parasitic capacitance? Parasitic capacitance which are connected with the output, right? Okay. Now parasitic capacitance, we have done an extensive study on this parasitic capacitance, but here, okay, for hand calculation we will only consider the diffusion capacitance. Can you recall the diffusion capacitance? Diffusion capacitance is the capacitance because of this n plus or p plus diffusion, between this n plus p and or this p plus diffusion and the other this base region, right? So here on this drain side you have one, right? Here also on this side you have one, right? So we will neglect the other capacitance. So here we'll write for hand calculation we will only consider diffusion caps, right? Okay, so no diffusion cap. So here we know 2 unit capacitance is been connected with the output node. Here 1 unit capacitance is connected with this output node. So total capacitance here is 3C, right? So how do you find this P? So P for this inverter we define it like this. Again, everything we define in with respect to this inverter only. So it is 3C by 3C. So the parasitic delay or this P for inverter is 1. Now using this concept, if we want to extend it here for this 2 input NAND gate, so we have already seen if the width ratio is like this, then the width ratio that we have already discussed here. So we will take the same width ratio because the reasons are already been explained here, right? So let us take the same ratio here. So it is 2, 2, 2, 2. Yes. So then can you comment what is the total capacitance here? Total parasitic capacitance here. Anyone? Akshay? Anubhav? Excuse me, am I audible? Yeah, Shubhayan, am I audible?
Yes, sir. Is it 5C?
You are saying it is 5P. So can you explain why you are saying 5?
Sir, basically all are 2C. So upper ones are in parallel, so that is 4C, and lower ones are in series. So that is
Right. So basically you see here all 2C, right? For this you will have one 2C, right? For this you have another 2C. For this also you have another 2C. For this 1 2C, 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 right? All are in parallel. So what will be the resultant capacitance? 6C, not 5C, Shubhayan, right? Shubhayan, am I?
So
Is this clear to you?
basically the lower ones, that I mean the NMOS which is connected to B, that is not connected to the Vout. That's why its capacitance is not considered, right?
Right, right. Because this one is not connected with this, Right. True, true, true. Here again we are doing couple of approximations. Truly speaking, you will also have some capacitance from this node to ground. Okay, so we are not considering this. So all these internal node capacitances are also being ignored, okay, for this hand calculation. As well, okay, only diffusion capacitance. Okay, so we will write here, not considering the internal node caps. There are internal node caps as well here, so we are not considering those. Okay, for example, you can see here also we have an internal node cap here, right? We are not considering this. Okay, okay. So similarly, right, if you have to scale this, so we can follow the same thing, 4 4 1 1. Technique is same for scaling the transistor, for scaling the PMOS and NMOS. 4 4 1 1. So it is 4, it is 4, it is 1, it is 1. So here 4 unit cap is being connected, and here 1 unit cap is connected. So total how much? Here 1 unit, here 1 unit. Total then 4, 1 plus 1. So total here also 6 unit. So here the parasitic cap is 6 by 3C. So that also makes this one equal to 2. Okay, so if you have understood this, then let me ask you one question from here. Find P for 3 input NAND. Can anyone tell what would be the P for 3 input NAND?
By
Sorry, could you please repeat
Sir,
again?
9 by 3.
9. Would it be 9?
8
2
by
plus 2 plus 3. 2
It
plus 2
will be
plus 2 plus
3.
3.
Some of you are saying 3, some of you are saying 9. Okay, let us see this. We have drawn here, right? This one. So see, what are the total capacitance connected with this output node? This is the output node. Here it is 2C, 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 3C. So it is 6 and 3, 9. So total is here, then 9C capacitance, or the parasitic capacitance is connected at the output node. So it will become 9C by 3C. So that makes this one as 3. Right. Similarly, if you do it for this case, you will find like for P for 3 like input NOR gate. Okay, please check it out. You will also get that will also become equal to 3. So then again, now we are plotting here the plotting means tabulating the value of P for different gates for different inputs. So first one is this inverter, second one is NAND, third one is NOR. So for inverter it is 1, for NAND it is 2, NOR 2 input 2, 3, 3. Here also if you make it 4, 4. So basically the number of input gates for this NAND and NOR, it should be the same as this. Fine. Is this part clear to you how to find? Okay. Then let's move to an interesting thing. So now, okay, before that, let me show you here. So see this equation, delay D is equal to P plus F, right? So now you know what is P for any gate, means at least the conventional gates. Now you know what is F is equal to G into H, right? So if this G you know for the conventional gates, and H depends on how many gates, suppose the same gates you want to connect with that. So considering this, let us try to do a small exercise. Let us say that this inverter is driving say n number of inverters. So same gates, should not be an issue, right? So this inverter driving n number of inverters, where this number of this n can change. Then the second case, it is a 2-input NAND gate. Say this 2-input NAND gate is driving again n number of NAND gates. Same. Okay. Right. Then we would like to plot this thing here. We would like to plot what is the total delay, means the normalized delay. Basically, we are not plotting the exact terms, means exact delay, but we are also normalized, means in terms of this TP not normalized. So in terms of this normalized delay, we want to plot with respect to the electrical effort. What is electrical effort? Number of gates, right? Number of same gates that you have connected here. Okay. So for this case, it is n, and I told you n can vary. So maybe this n can be 0. This n can be 1, 2, 3, 4 n number. Same for this. So could you please help me in plotting, in completing this plot? Okay. So let us start with this inverter. Okay. Let us fix this inverter. Inverter is for color. Say we have fixed this pink color. So for this inverter, say this inverter is not driving any gate. So it is n is equal to, so let's say n is equal to 0. So not driving any gate. So this single inverter. So when this inverter is not driving any gate, then as per this equation, that is D is equal to P plus GH, right? H is equal to 0, right? So this term becomes 0. So D become equal to P. This D become equal to P, right? Okay. So what is the P for inverter? Parasitic delay.
TP not.
It's 1, right? So it's 1. So this value is here. This value is here 1, right? Normalized delay 1. So let us also, looks better. So we are trying to mark it. Right. So this is the parasitic delay. Means if you have any load on no load, this like 1 unit delay will always be there. Right. Okay. Now, what will be the delay when this n become equal to 1? So n equal to 1 means basically h is equal to also 1. I hope you can recall that, because h is equal to C out by C in. Right. So here C out and C in becomes equal, so that makes h equal to 1. So it is basically then 1 plus GH. Okay. So basically then for inverter, this equation is transformed to D is equal to 1 plus, what is the G value for this inverter? It is 1. H is variable, so this H is this. So you can see this basically a straight line equation, right? Straight line equation, and the slope is also equal to 1. This intercept is also 1, that we have fixed. So then we have to if we have to plot it, so basically at 1 it will become 2, at 2 it will become 3, at 3 it will become 4, right? At 4 it will become 5, at 5 it will become 6, right? So basically we should have a plot like this, right? So this is for inverter, right? Where G is equal to 1, H again H can change, P is equal to 1, right? And that makes H this equation. Okay, so it is pretty easy to understand, right? Okay, but remember here one thing, in this plot, at this output you have connected the same logic gates. Okay, now let us focus on this. Now it is NAND gate. Right. So again, for NAND gate, this same equation will become, what is the delay for 2-input NAND? It is 2, right? What is the G value for NAND gate? It is 4 by 3, right? Into H. So what is 4 by 3? This is slope and this is intercept, right? So fix it to, right? it is 4 by 3. 4 by 3 is greater than 1. So the slope for this would become like higher. Again, I am just plotting it. I have not calculated for what value what should be this, but yeah, it's typically it should be like this. The slope should be higher than this, and this is the parasitic delay for this NAND gate. Two input NAND gate. Here this G value is equal to 4 by 3, P is equal to 2, and that makes D is equal to 2 plus 4 by 3 H. Right? So then if you want to find like at any moment what is the like parasitic delay and what is the effort delay, so say for this case, right? Okay, it, right, H cannot be and this part, so H cannot be a fraction, so it can be say like this. Okay, so this much, okay, this much is the not this, not this, this much, right? This much is the parasitic delay for to input NAND. This much is the effort delay. Have you understood this? So for any age, you can now explicitly find what is the delay, means what is the parasitic delay. Anyway, parasitic delay, you know that it is always the same for two inputs, so you can know it's always 2, right? But it's a type of graphical representation, right? Okay, so I think it's already 12:53, so probably we cannot. Yeah, any doubt so far here? Because I was thinking that then we will do this, but if we start, I think we cannot finish it. No. So here what we are trying to do means now we have understood what would be the G means parasitic delay for different gates, what is the logical effort for different gates. Now for this for this combinational circuit, what should be the size of this X and Y and Z such that the delay would be minimum. Okay, we are trying to find now this, right? Okay, so I think in tomorrow's class we will start this, because anyway if I start then I cannot complete, and again tomorrow we have to start, restart. Okay, so yeah, if you have any doubt here.
So that is effort delay for
Shubham, actually it is not the Elmore delay. Elmore delay we will be going to covering, and there Elmore delay we will cover. Okay, there we will also see, we will consider this one. Okay, right, we will consider the internal node capacitances as well.
I was talking about the graph. That is the effort delay basically changes with n, right?
You okay? You are saying effort delay. Yes, it is the effort delay. I heard it is Elmore delay. So we have something called the Elmore delay model also. So we are going to cover. So I thought you were talking about that. Yes, this is effort delay, right?
So this basically changes with n, right? There is a
This
number of
yeah, this basically
changes with n.
this basically depends on n, right? Or the fan out.
Okay, okay, sir.
So fan out, see, when you say this fan out, here for this case the fan out is n, right? But if you like consider some case, say like this inverter driving one in this not inverter, this NAND gate driving one inverter, okay, another this gate, maybe two this gate, one say, okay, say maybe this XOR gate. Okay, so XOR and all these things maybe we can like discuss later on, right? So in that case, how do you find this like H? It is then in that case you cannot say like because the gates are different, right? So here you have to find what is the total capacitance here, make the input capacitance here, and you know that what is the input capacitance here. So like that whatever we are discussing here, right? You can see it. So it's basically the C out by C in. What is the total output capacitance and what is the total input capacitance. Anyway, we will see these things, okay? We will see these things. So first we will discuss tomorrow, start with this one. So here, right? So here you can see we have only one path. We have only one path from here to here, right? But it can also happen that maybe you have also one more path here. Right. So that means you have some branching here from here. So let us first discuss without branching, the very simple case. Okay. Then we will also introduce these other parts, like what will happen if we now introduce branching right from here. Because in any particular like design, right, you can have a structure or in the circuit diagram like this. So then what to do? Okay. How should we handle that? Okay. So that we are going to discuss tomorrow. Okay then. Thank you. So we will meet again then tomorrow.